All right. Good evening. So I'll be discussing chemistry, but before we start, let me just share Philippians 4:13 that I can do all things through Christ who gives me strength. So whenever you feel weak, just remember this one, Philippians 4:13, and yeah, God will surely renew your strength because you can do all things through Christ who gives you strength. Yeah. Amen. So here's the topic, chemistry. And by the way, I'm Engineer Rainilan L. Dimal, or you can call me Sir Deems. So for chemistry, this will be a 3-hour lecture, but I'll be cutting it into two portion so that it will be longer. And but I'll try to discuss it even faster so that we'll have a minimal length of the video. And um, anyway, I should start so that it will be shortened. So chemistry is the science of matter. It is the study of its composition, structure, properties, and chemical reactions. So these will be discussed later on. The composition, the structure, properties, and chemical reaction. Um, Before we dive into those discussion, let's consider who's the father of chemistry. He is Habir ibn Hayyan. Okay, he actually introduced chemistry. Not all the elements, but the elements like earth, fire, water, air, ganun. But anyway, what you know about chemistry nowadays is the modern chemistry, Antoine Lavoisier or Lavoisier. So he introduced the periodic table. So that's why he's called the father of modern chemistry. But again, if we go back to the father of chemistry, he's Habir ibn Hayyan. And then modern chemistry, it's Antoine Lavoisier. So everything about chemistry is matter. So matter is anything that occupies space and has mass. It it is anything that has density. It commonly exists into three phases: solid, liquid, and gas. When when we study chemistry, this is always the uh, a definition that we don't forget, the matter, right? And basically, the phases, solid, liquid, and gas, are also common. But nowadays, I'll introduce two more phases of matter. We'll discuss it later. Okay. So let's talk more about the phases of matter. We'll start with solid, which is composed of particles that are tightly packed and have a regular arrangement. It has a definite shape and volume. So as you can see in the figure, the particles, we'll discuss them later. Um, these particles are tightly packed or they are connected with each other. So that's why we call them solid. An example of solid is a wood, a plastic, um, anything that you can hold, something like cell phone or laptop, those are solid. And then we have the liquid. It's composed of particles whose arrangement and packing are somewhere between those in solid and gas. It has a definite volume but no specific shape. We usually term it as it takes the shape of the container for the liquid. So we know an example of liquid is water, juice, any other liquid like soft drinks. The molecules, or say particles, are separated comparing to that of the solid. They're which in solid they are connected with each other, but for liquid they are somewhat not connected. Okay, that's why basically we can't hold them steady. So it'll just flow into our hands because, for example, water, something like that. And I know you're familiar with liquid. Let's go now to gas. It's composed of particles with no regular arrangement and no appreciable packing. It has no definite shape or volume. It takes on the shape and volume of its container. So the particles here in gas are now separated. They are separated with each other, and we can't we can actually somehow see other gases, but sometimes or most of the time we can't see them. An example of gas for the matter is air, the oxygen, the carbon dioxide. Those are gases. So I know again you're familiar with these three. Let's just move on to the next one. But before we go to the fourth one, which is I'll introduce later, let's talk about first the phase changes. And I think y you'll be familiar with most common process like solid to liquid. It's called melting. An example of that is an ice to water. It's melting. Solidification is the reverse of that process, which is from liquid will turn it to solid. Like for example, water will turn into ice. That's solidification. Evaporation is an example of, or the phase change for evaporation is liquid to gas. Like for example, you boil the water, so water will now change into gas. They evaporate. Okay. Now there's a term that we used when we reverse the process of from gas to liquid. We call them condensation. Okay. So it's an example of um, gas turning into liquid. So most of the time you can see them, for example, you have a dehumidifier. Okay. The dense air molecules will now filter and it will be converted into liquid because the humidifier is collecting the air molecules or water molecules into the air, and then they convert them into a known liquid. That's an example of condensation. Now, sublimation is the phase change directly from solid to gas. Okay, so solid to gas. A good example of this one is the one that you place in the bathroom. Most popular brand is Albatross, wherein the that's a solid, wherein it's like a perfume in the bathroom, and then it will not change to liquid, but it will basically convert into gas directly. That's sublimation. Okay. So the last one is somehow very difficult to explain, but sorry again. It's a deposition wherein you are turning gas to solid. Okay. So how do we remember this one? I actually don't have an example of deposition. I have actually, but it's quite uh what do you call this? I don't like to share it, guys, but well, maybe I can tell you what deposition or what my example of deposition is. So like for example, your uh you have a stomach ache and then you're farting a lot. that's gas. But when you fart and there's something solid came out, that's called deposition. Okay, that's an example of deposition. I'm not sure if you will laugh about that example, but that's how I remember the deposition. It's like it's gas and it turns into solid. Okay. Now we'll go to the uh, fourth phase, which is the plasma. So a state of matter similar to gas in which a certain portion of the particles are ionized. So nowadays we have plasma, the fourth um, fourth state of matter, which is nowadays we are using them to, let's say, cut something like in plasma cutter. Anyway, it was discovered by William Crookes in 1879, but Irving Langmuir coined the term plasma in 1928. Okay, those are the three terms that will be considered very important, like when you encounter a problem or a question in in general engineering and applied sciences, you'll see the one of the question will be it's a state of matter similar to gas in which a certain portion of the particles are ionized. The answer for that is a plasma. Okay, that's the fourth one. And then another one is the BEC. What's a BEC? It's a Bose-Einstein condensate. Okay, it was discovered by, well, definitely it's a well, it was discovered by Bose and Einstein. That's why it was called the Bose-Einstein condensate. It's a gaseous superfluid phase formed by atoms cooled to temperature very near to absolute zero. So through the advancement of the technology, or not really in technology, but they can cool up to a temperature to absolute zero, and that's a negative 273 degrees Celsius. And they say that when they reach that point, even the electrons will stop spinning. So that's my what do you call this? That's how I remember the BEC, the Bose-Einstein condensate. So Satyendra, not Bose and Albert Einstein, the first people to predict, but it was produced in 1995 by Eric Cornell and Carl Wyman. Okay, so these two people are the ones who made it, but they are giving the credit to Bose and Einstein because they're the first one to predict the the presence of the superfluid gas. Okay, so after that, the matter. Let's talk about the very small particle, which is the atom. So it's the particle that I mentioned about when we define the solid, liquid, and gas. So it's a basic building block of matter. It is the smallest particle of the element. So we call it particle, but it's the smallest of an element. So what's an element? It's a fundamental type of matter in which all of the atoms in the material are the same. So an example of element is oxygen, element of hydrogen, element of chlorine. So when you see, for example, or you don't see oxygen, but in terms of oxygen that we breathe or inhale, we have a lot of atoms of that oxygen. But the smallest particle of that element of oxygen is called the atom. Okay. Now, we have fundamental chemical laws, the law of conservation of mass. So Please remember this one. The first law of conservation of mass is neither created nor destroyed. So you are actually conserving the mass. That's the first fundamental chemical law. And then the law of definite proportion, originally called Prost's law. So a given compound always contains exactly the same proportion of element by mass. So even if you increase the atoms, you'll still have the same proportion of elements in terms of its mass. Okay, that's the law of definite proportion. And then number three is the law of multiple proportions. When two elements form a series of compounds, the ratios of the masses of the second element that combined with 1 gram of the first element can always be reduced to small whole number. We'll be talking more of these multiple proportions um, when we're solving the empirical formula, something like that. Okay, just remember the definition is um, when you combine 1 gram of the first element, it can always be reduced to smaller or whole number. Okay, let's talk more about that later. So here's the atom, but the atom is composed of what we call neutron and proton. The combination of neutron and proton is called the nucleus. Okay, so for example, the blue portion or the light blue is your proton. They're combined with the neutron. We call it nucleus. And then electron is the one that are spinning outside the nucleus. So electron is very small compared to proton and neutron. Well, actually, you can use the calculator to check the mass of these using the constant. So when you try to place constant 0, 1, you'll see the mass of proton equal to 1.67 multiplied by 10 raised to negative 27 kilograms. This is in kilograms. So if you go to constant 0, 2, it's almost the same, the mass of neutron. So mass of neutron is somewhat a bit heavier compared to proton. So look at this. Proton is 1.6726, but neutron is 1.6749. Both in the times 10 to the power of minus 27. So when we go to the electron, constant 0.3, you'll see that its weight is around 9.11 times 10 to the power of negative 31, which is a little bit more, I mean, it's a lot lighter than proton or neutron. So one of the question the board exam, I guess, it's what's the ratio between the mass of proton and electron? You just simply divide the constant 0, 1 divided by constant 0, 3. Then there you have their ratio. It's around 1,836 times heavier. So mass of proton is 1,836 times heavier than the mass of electron. It means that when you have 1,836 electron, that's equivalent weight of one proton. That's how proton is heavier than electron. Okay? So let's talk about terms like atomic number and mass number. Atomic number of an element is the number of protons that is contained in the nucleus of its atom. So when you see the periodic table and then you are seeing atomic number, that's how many protons the element has. Like for example, hydrogen. Hydrogen is the first element. It has an atomic number of 1, and it means that it has one proton. Helium is atomic number 2. So it means that it has two protons. Okay? And so on. So Mass number or atomic weight is the sum of the number of protons and neutrons in the nucleus of the atom. So, as I've said earlier, when you see the image, um, technically the weight of the proton and the neutron is almost the same. So when you're trying to weigh one atom, the electron is basically negligible. Even if you have a lot of electron, like for example, you have 100 electron, that won't give an effect on the weight of the proton and the neutron. Okay, so the mass number or atomic weight is the sum of the proton and neutron in the nucleus. Okay, you'll be seeing this in the periodic table, like for example, helium. Um, as I can remember, for helium, its atomic number 2, but the mass number or atomic weight is 4. It means that it has 2 proton and it has also 2 neutron. Okay? Or for example, you go to oxygen. Oxygen is atomic number 8, but when you weigh it, it's 16. How come it's 16? Because it has exactly the same number of neutron and proton. So that's why it has 8 proton and 8 neutron. The atomic weight of oxygen is 16, if I can remember it right. And here's one very weird phenomena. It's in the periodic table of element also, which is the hydrogen. When you see the hydrogen, it has atomic number 1, and the atomic weight also is 1. How come? It's not 2, right? Because in all elements, there's only one element that originally doesn't contain any neutron, and that's the hydrogen. Right? If it has a neutron, it'll be an isotope of the uh, hydrogen. We'll talk more about the isotope later. But for now, just remember that hydrogen is atomic number 1. Atomic weight also is 1. It has no neutron on its basic content. Okay? So let's try to review some questions. You can pause it while before I answer it so that let's check if your answer is correct. So all forms of the matter is composed of extremely small particles called what? Okay? Extremely small particles. So these particles are called, of course, these are atoms. Okay? We'll discuss more of molecules later, but electron is part of the atom, right? But we're talking about matter. So matter is composed of these small particles, we call them atoms. Okay? Next. The process in which a solid changes directly to its vapor without first forming a liquid is called, oh, remember I told you that this will be as eventually. So it's solid change to gas. So what do you call this? If you go back to the video, you'll be seeing that we call it sublimation because it's an example of like albatross, if you can remember, or if you watch it. I mean, next, the state of matter which occupies the whole space available. Sometimes students will confuse about the answer for this one. Well, they'll be saying that, oh, D is the answer because gas can occupy the whole space available and also liquid, but actually only gas. Because sometimes, even if you have filled out the available space for a given liquid, there's always air molecules, or I mean, always a space that won't fit on the liquid, or I mean, there's a space for that closed surface. So liquid cannot always occupies the whole space available, but gas always is. Okay? So we only answer letter B here. Next, which of the following falls under fluids? So when you say fluids, these are movement of molecules. And this time, I think both B and C is correct. Okay. So fluids, liquid can be a fluid and gas can also be fluids. Okay. Fluids is the motion of the molecules. When you say fluids, we're not talking about liquid only. We're also talking about gas. It's the movement of these state of matters. Okay. But solid, you can't make a fluid out of solid. So the answer for this one is letter D. Next, a property of matter which can be measured without changing the identity and composition of the substance. It's a property. We didn't discuss yet about the property, but it was asked here. So maybe we'll try to understand more about property later. But for now, what do you think is the answer? Which can be measured without changing the identity and composition of the substance. So you call this the physical quantity or physical property. I mean, we're not changing the identity and composition. So, uh, like for example, a physical change and compare it to a chemical change. Chemical change we will be changing the identity then when you do a chemical change, but a physical change, not really. We're not changing the identity and the composition of that substance. Okay? Extensive and extrinsic, maybe we'll discuss this when we're discussing about thermodynamics, but for now, let's move on to the next problem. Which of the following is not an extensive property? Speaking of extensive, letter B here. So what do you mean by extensive property? I guess we'll be discussing it now. So there are two property about extensive, and we also have the intensive property. I guess these are chemical properties, which are branched into two, extensive and intensive. Well, what do you think is not an extensive property? Okay, so length, melting point, volume, and weight. Okay, so with I'm not really sure what's the answer for this one, but if I can remember by elimination of like length, volume, and weight, these are measurable values. Melting point is not, um, for me, it's not really a measured value. It's the point where your ice will melt. It's the temperature. It's the value in temperature. So I think I might guess this one, but for me the answer is letter B. Let's check it out. Oh, see? So that's a good example of trying to guess what's the answer, but it will be based on the other choices. Because the question is which of the following is not an extensive property? So basically length, volume, and weight, these are extensive property. And melting point is somewhat doesn't belong on the group. Okay, so that's how I guess the answer, and it's correct. So lucky me. Okay. Number seven, with water is an example of a reaction with water is an example of a physical property, a chemical property, endothermic, exothermic. I guess endothermic and exothermic will be discussed in thermodynamics. I'm sure of that. But for now, let's a reaction with water is an example of what? A physical or chemical property. Like for example, you mix sugar with water. So what happens with the sugar? It turns into liquid, right? So you can't identify the the substance already changes. It comes from solid and it becomes liquid now. So I think for me, the answer for this one is chemical property. Let's check it out. See, that's a chemical property. When you do a physical property, you can still identify the substance, even it changes. Okay. Oh, I guess these are the uh, summary of the property. So for the oh, physical property will be branched into two, the intensive and extensive. I apologize if I mentioned about chemical property that was branched into extensive and intensive. It should be the physical. For chemical properties, how does the substance react in the presence of air, acid, water, base, and other chemicals? So when you don't identify the original substance after it was reacted into air or acid or water and other chemicals, it's basically undergone chemical property. But for physical property, we have two. We have the extensive, which we have dealt about earlier. The, the mass, the volume, the length, the shape, these are extensive. Okay. But intensive does not depend on the amount. So like color, taste, melting point, so which is our answer earlier, boiling, density, luster, hardness. You might think why density was part of the intensive property because you know that density is mass over volume. So basically it was a ratio of the two extensive property. You're like canceling the units of mass of kilogram and volume in, let's say, meter cube, something like that. So basically density is, you call it unitless when you're canceling the unit of mass and volume. So density is part of the intensive property. Okay. So number 8, a substance, all the atoms of which have the same nuclear charge. Okay. All of the atoms of which have the same nuclear charge. So this is what I mentioned earlier. Like for example, you have an element of oxygen. It composed of a very small particles called atom. And when you combine these atoms of oxygen, the combination of those multiple atoms is now your element. But technically, that element is still neutral. Neutral is the same nuclear charge, meaning if you have the same amount of proton, that will be the same number of electron as well. If you have 8 proton, you have 8 electron. So the atom is electrically neutral or nuclear charge. So that's letter A. Element, the answer for number 8. Next. Oh, so this is the definition of element, chemical substance that is made up of unique kind of atoms and cannot be broken down into simpler substance. Compound, what's a compound? Pure chemical substance consisting of two or more elements combined chemically. So like water is a compound. It's a combination of oxygen and hydrogen, something like that. That's your compound. What's a mixture? There are two or more different substances which are not mixed chemically. We have two types of mixture. We have the homogeneous mixture and heterogeneous mixture. Mixture that is uniform in appearance and has only one phase. Uniform in appearance and has only one phase. Like for example, you mix salt and salt and sugar. They appear in the same phase in solid, but you basically mix both of them. So that's a homogeneous mixture. Heterogeneous mixture is mixture that has distinguishable phases. Like for example, you mix salt with pepper, or I mean distinguishable phases pala. So it's they're both solid. So like pepper and vinegar. Okay, so that's an example of heterogeneous mixture. You see that the mixture is now Pepper is in solid form and vinegar is in liquid form. Okay. Take note that mixture is not mixed chemically. So we're not dealing about sugar mixed with water. So that's a chemical mixture. Or but for this mixture alone, we're dealing about mixture of different substances like potato salad or like vegetable salad. These are mixture. Okay. So okay. Number nine, atoms of an element having the same atomic number but different mass number. All right, so this is what we call having the same atomic number but different mass number. So why do you think we have different mass number here? Because it still has the same atomic number, meaning you still have the same number of proton but different number of neutron. Okay, so that's I think I mentioned this earlier. It's called isotopes. Okay, so the definition of this one is the same proton number. That's why it's called P. Same proton number, but different neutron number. As I've said earlier, for example, hydrogen. Hydrogen has only one proton, but it doesn't have originally neutron. But there are isotopes of hydrogen, like we call it protium. Protium is one of the isotope of hydrogen, wherein it has one proton and it has one neutron. And we have another isotope of hydrogen, we call it deuterium. It has two neutron and one proton. It's still hydrogen, but it has now two neutron. So its atomic weight is now three, not just one. Okay, the protium has atomic number one, but the atomic weight is two because it has one proton and one neutron. And then we have tritium. I guess tritium has three neutron. Then afterwards, the other isotopes, we call them hydrogen 4, hydrogen 5, hydrogen 6, and so on. Isotones, on the other hand, is the same number of neutron but different number of proton. Okay, they may have a different element name, but if they have the same number of neutron but different number of proton, we call them isotones. Okay, I don't see an example of this one, isotones, but I know the definition of that because of the name itself, since isotones, N is constant here. For the isotopes, P is constant here, so number of proton is constant. Okay? Oh, see, there's a designation. Isotopes equal number of proton number. Isotones equal number of neutron. Isobars is equal mass number. So I just forgot about this one, but there's also a term we call it isobars, equal number of mass. Okay. Oh, so this is what I mentioned earlier. The isotope of hydrogen is also known as the protium, tritium, and deuterium. So all of these are isotope of hydrogen. Just recall again, protium contains one proton number and one neutron. Tritium is one proton, three neutron. Deuterium is one proton, two neutron. Okay? The atoms having different atomic number but the same mass number are called same atomic number but the same mass number. This is called different atomic number but the same mass number. So when you say the same mass number, um, you're not technically saying that it's number of neutrons. So I guess this is homologous, although I'm just guessing about this, but I can say it's letter B. So cross fingers. Oh, it's isobars. Oh, okay, same mass number pala. Okay, it was already mentioned earlier, so I apologize for that. Same mass number, is called isobars. Yeah, right. It was already mentioned here. Here, equal mass numbers. So I just forgot about it. I just read it and then I forgot about it. So I'm really forgetful nowadays. Number 12. The concept that electrons revolve around the nucleus in a specific path called orbits or angular level was proposed by. So if by process of elimination, Rutherford is the one who discovered proton, I guess. Electron is J.J. Thomson. J.J. Balmer is I don't know who's this guy, but Niels Bohr. That's why we have the Bohr model for the nucleus. So this is our answer. Okay. The mass of electron is blank times the proton. So I remember we tried to solve this one earlier. It's just a reverse computation that we did, the proton divided by the electron, their masses. So if you can still remember, our answer is letter B. It's 1,847, I guess. But what we computed earlier is around 11836. Oh yeah, 1836. But for us, closest one is letter B. I hope it's letter B. Okay, it's letter B. So it's 1 over 1,847 times. Okay? The net electrical charge of an atom under normal state is. So this is what I mentioned earlier. By the way, earlier I just realized that I'm talking about neutral charge, but the statement is nuclear charge. So anyway, these are the same concept as well. So we'll be considering it's neutral. Okay? So neutron was discovered by whom? So by process of elimination, we will not be considering Einstein, okay, because he discovered the theory of relativity. So we'll just it's either A, B, or C. So J.J. Thomson is for electron. So Goldstein or Chadwick, Goldstein or Chadwick. For me, it will be Chadwick because I remember Goldstein was also the one who discovered proton, but again, let's check it out. So it's Chadwick. So for Chadwick, it's Chadwick discovered neutron. Goldstein was also discoverer of proton, and electron is for J.J. Thomson. Just remember J.J. J.J. is like for electron. J.J. it's is the one who is very um always circling around, always moving a lot. That's why I remember JJ as Electron because I know someone whose name is JJ and he moves a lot and he talks a lot. That's why I called Electron. Anyway, that's a joke. Electron was discovered by whom? Okay, we know that it's now letter A. It's JJ. And again, if the proton was questioned, it's either Rutherford or Goldstein. Okay. The number of neutron in an atom of chlorine with mass 37, atomic number of 17. Okay. This is easy because your mass number is 37. The atomic number of chlorine is 17. You just subtract it. So basically, 17, you need to have 20 neutron in order for you to get the mass of 37. Did you get the point? Yes. So that's the answer, letter A. So why did we use the calculator? Okay, we will be using the calculator. So 37 minus 17 is 20. Okay, satisfied? All right. Okay. Now we go to chemical calculations. So for the chemical calculations, I guess after we finish chemical calculation, we'll have a break and then I'll cut the video, upload it. Then I'll create the next part of the chemistry. Okay, so the first chemical calculation, which will be very important in the board exam, plus your exams in school. So it's atomic mass or atomic weight is the average of the element's isotopic masses. So that's the mass multiplied by the percentage plus another mass multiplied by another percentage and so on. We'll have to an example of this one later. Next, formula mass or formula weight is the sum of all masses of all atoms in a given formula. Is the sum of all masses of all atoms in a given formula. We'll have an example of that also later. And then a mole concept or molar mass is, what is a mole? It's the amount of pure substance containing the same number of chemical units as there are atoms in exactly 12 grams of carbon-12. So, well, basically, when you say atomic mass, um, for example, this carbon, it's as carbon-12. Okay. So the meaning of carbon-12 is that it has 6 proton and 6 neutron, right? But the other term for that 12 for carbon is also the atomic mass unit, or also known as the grams per mole. Okay. So 1 mole is now the ratio of this number of grams to this atomic number of carbon. So basically, we'll have more of that later for mole. Just remember about the atomic weight unit is also known as the gram per mole. Okay. So naturally occurring magnesium consists of 78.7% of magnesium 24 with atoms of 23.98504 mole. This is what I mentioned about the gram per mole earlier. Atomic mass unit is also the same with a unit of gram per mole. Okay, so this is almost 24 grams in 1 mole of magnesium. So that's why it's called 24 magnesium. And then it has 10.13%, or sorry, 10.13% of magnesium 25 with an atom mass or atoms of mass of 24.98584 and 11.17% of magnesium 26, and this is the atoms of mass or atomic mass. Calculate the atomic mass of magnesium. So if you try to add all of the percentage given, so the 78.7 plus 10.13 plus 11.17, this should be around 100%. And that's why it's 100%. So for the magnesium now, we will be using the formula mass multiplied by its percentage. And that's it, mass times percentage and mass times percentage. So I won't be writing it down using our whiteboard. I want to try to use this whiteboard now, but I can just use the calculator to solve this one. So it's 78.7% multiplied by its mass, or we'll start with M1P1 23.98504. Okay, multiplied by 78.7% or 0.787. Okay, so then plus 24.98584 multiplied by 11.17%. It should be 0.1117. And then plus 25.98259 times Oh, wait. Okay. 20 point. Wait. It's 24 multiplier. It should be 10.13. 1013. And then the other one will be multiplied to 0.1117. So our answer should be around 24.13. Okay? Now, I want to share to you that you can solve this one also using variables. Let's say A, B. Okay? So now, when you calculate, it will be ask you the value of A, that's your mass. Just type in 23.98504. Then you'll be asked B, that's a percentage, 0.787. Ideally the same concept, but this time you you store this one to M. Shift store to M. Then you calculate again. So this value now was stored to M. Then when you calculate your AB again, you move to the mass 1 or the mass 2, 24.98584, and then 0.1013, that's your 10.13. Okay, now you need to add this one to M. That's the purpose of M plus. So just press M plus. So meaning of M plus is original M plus this one will be your M plus. So if you recall M now, alpha M, that's around 21.4. But you're not that yet done because you still need the third value. So calculate this one again to 25.98259 and then 0.1117. Then press M plus, then recall M. That's still your answer. Okay. So how come I mentioned about that computation? Well, in reality, when you're taking the board exam or when you're taking any exams, you should know how to use your calculator properly. Because it will lessen your time of computation. So you might be asking, well, sir, you just solve it a lot longer than I just type it. Well, actually, I'm explaining it while I'm solving it. But if you can see, like I just try AB and then calculate 23,98504 0.787 stored to M, then calculate again. So 84 0.1013, then M plus, and then if I have my physical calculator here, this will be a lot faster. 98259 0.1117. Recall M. That's 24.32. Okay? Well, it's your choice if you want to use this one or not. Let me just go to the next problem. Calculate the percentage of bromine atoms that have a mass of 78.9183 atomic mass unit, and the percentage that has a mass of 80.9163. The atomic mass of bromine is 79.909, and these are the only two naturally occurring isotopes of bromine. So how do you get this one? Basically, when you do the formula, you'll be having M1P1 plus M2P2 equal to your atomic mass unit. Okay, so when you try to place this one, 78.9183 P1 plus 80.9163 P2, and the atomic weight of bromine or atomic mass is 79.909. you'll see that you have two variables P1 and P2 while you only have one equation. So how do you do this one? Well, I'm just seeing only one possible solution here is that you place this one on your calculator, like type it 78.9813, then place A, then plus 80.9163B. Okay. Then you calculate it. Then A and B are your percentage. Like for example, I place it 10% or 0.1 and then 0.9 for B. I got 80.72, which is what we need is that your atomic mass number must be 79.909. And we will be using not 10% and 90%, but rather your choices. So let's try calculating it to 0.504 and then 0.496. It's 79.94941. Okay, let's try to go to next one. 0.624, 0.376, 78.709, 0.554, 0.446, 79.84, not the 79.909. So 0.346, 0.654. 80. So we don't have an answer. But we just consider that this 50.4 is for this percentage. So we can actually try to reverse it like your 49.6%. So 0.496 will be multiplied to this first mass, and then 0.504 will be multiplied to the second mass. We have 79.956, and then 0.376, 0.624, 80, and 0.446, 0.554, 80 again, 0.654, 0.346, 79.65. So I guess the one that is closest is this 79.9. Earlier, we also got that same 79.9 from this percentage. So I'm thinking that these might be the answer, letter A. All right, that's how you get it. But maybe we just didn't get the exact 79.909 because these percentage now are rounded off. Okay. But I'm not seeing any other solution here. So I guess that will do it. Number 19. Now determine the formula mass of aluminum chloride. So aluminum and then chlorine. So for the formula mass, you should know the individual atomic mass of our element. Like for example, chlorine. I think chlorine is 30, 35. So if we have 35 for chlorine multiplied by a subscript of 3, we already have 105 for chlorine. How about aluminum? So I can't remember the weight of aluminum, so I don't have any other way on how to answer this one. Let's check. Oh, aluminum is 27. So it is in the presentation, guys. So 27 for aluminum, chlorine is 35. This is I remember, 35.45. So I should be placing 0.45 here. Then plus 1 aluminum is 27. So that's how you get your formula mass. You just add basically the weight. So I apologize if I can't remember the aluminum, but that's the purpose of the presentation. Okay. So now I'm thinking that what happens if you don't remember the aluminum? Well, supposed to be you should be memorizing the common elements that were used in the most of the problems in chemistry. One of them is aluminum, and most of them is chlorine. So other elements that are used are oxygen, that's a 16 atomic mass unit, nitrogen 14, carbon 12, hydrogen like it's only one, and so on. Just try to memorize as much as element and atomic number as you can so that you'll have an advantage when it comes to the problems in chemistry. When I took the board exam, I remember I memorized most of them. But right now, it's been around 15 years, guys, so I can't remember the aluminum. But again, that's the purpose of the presentation. So thank you, presentation. So another chemical calculation is Avogadro's number. Here, I'm not sure how Avogadros count this one, but he says that the number of particles in 1 mole is 6.02 times 10 raised to 23. So he's a very patient guy. He counted a lot of the particles, so that's why it's called Avogadro's number. So it's a 6.02 times 10 to the power of 23. Wow. Kidding aside, guys, he just computed it, but that's how I remember Avogadro's number. It's actually a constant also in my calculator, so I just can't remember what number it is. So let's say 24. Oh, luckily I got it, guys. It's constant 24. So shift constant 24. So just place 24, then boom, it's 6.0. So it's on my reflexes still. Your NA is 6.02 times 10 to the power of 23. Okay. So how do we convert it? Later, I'll show you how to get the number of particles in a given mole. And then the mole mass conversion is the formula for calculating mole grams or gram formula mass, also known as a molar mass. And the number of moles is this one. Okay. So just remember that M is your mass. Like for example, the mass of carbon is 5 and it has an atomic mass number of 12. So you just divide it, you'll be getting the number of moles. Okay? Say 5 over 12 moles, which is what I mentioned earlier. So for a 12 mass of carbon or 12 grams of carbon divided to 12 gram per mole, that's equivalent to your 1 mole. Okay? So that's the definition of mole earlier. I'm not sure if you're familiar with it, but if you heard what I said earlier, but then again, the number of moles is mass over M, and M is your molecular weight or your atomic mass unit. So if you see in terms of unit, like this will be in grams, and molecular weight is grams per mole. So grams will cancel, and the unit of N will be moles. Okay? So let's talk more about that later when you have an example. And then this is the mole number of particle conversion. So 1 mole contains 6.02 times 10 raised to 23 particles, which is equivalent to what Avogadro's number is, or what does the very patient guy did. He count them. Okay, that's a joke again. And then equivalent weight. The equivalent weight is the amount of substance that supplies 1 gram mole, that is 6.02 of the reacting units. So this oxidation number will be given as well. Then you just get the molecular weight or the atomic mass unit divided by your oxidation number. If not, well, good luck if the oxidation number is not given. It's actually in the periodic table. So I'm not sure if you need to memorize them as well. So like for example, number 21. What is the mass of 5 moles of NH3? Okay, so NH3. What is NH3? Ammonia. So hydrogen contains um, three substance. So that's a 1 atomic mass unit times 3. You have 3 ammo for the hydrogen. Then nitrogen only contains 1, but the atomic mass unit for nitrogen is, as I mentioned earlier, it's 14. Because its atomic number is 7, it has also 7 neutron. So 7 plus 7 will be 14. That's how I remembered nitrogen. So this will be 17, or sorry, should be 14. I'm just excited about the total. So it's a 17 atomic mass unit. Okay. And as I mentioned, these atomic mass unit is also the same with 17 gram per mole. So this is your NH3. And the question is, what is the mass of 5 moles? So it has 5 moles. So you just basically multiply this by 5. Or your 17 gram per mole, multiply that to 5 moles, canceling number of moles. You have 70 times 5, that's an 85, I guess. Or let's just try to use your calculator. All right, that's a 85. So our answer is letter C. Okay, next. Calculate the number of molecules in 57.6 grams of NH3. The same ammonia that we have an example earlier, but this time the mass is given. We don't know the number of moles. So number of moles is mass over molecular weight. Oh, sorry. I just pressed the next one. So anyway, the mass is 56.7, 56.7 grams. How about the molecular weight? We have solved it earlier. It's 17. So we divide this one with 17 gram per mole. We'll get the number of moles in terms of moles. So using my calculator, it's 56.7 divided by 17. All right. It's around 3.3 mole, 3.335. But how do we convert it earlier in terms of number of particles? So 1 mole is not available. Or, sorry, it's an Avogadro's number, which is 6.02, 6.02 times 10 to the power of 23. Or just use your calculator, constant 25. So times constant 25 or 24? I guess it's 24. Yeah, 24. It's around 2 times 10 to the power of 24. All right, so this is a 2.01 times 10 to the power of 24. Okay. Now we go to number 23. 1 mole of carbon dioxide contains, it's already given, it's in 1 mole, not in grams, not in molecular weight, so it's 1 mole. And 1 mole is basically equal to the number of particles by Avogadro's number, right? So 6.02 times 10 to the power of 23 carbon 6.02 times 10 to the power of 23 of oxygen, or 18.1 times 10 to the power of 23 of carbon dioxide. And this is equivalent to 3 grams of carbon dioxide. All right, so this is a challenge now. So carbon dioxide is carbon 12. Okay, what? Carbon 12. And oxygen is 16. Well, we won't need to compute its atomic mass number because it's already, hmm. Okay, I guess the answer here is letter A. How come it's only carbon? So it's only carbon because oxygen, we won't be counting the oxygen here. We only considering the number of carbons. So that's basically your number of moles, or 1 mole is the same with Avogadro's number. And we're only considering the number of carbons, not in terms of oxygen. Okay. Then determine the percent composition of nitrogen in NH4NO3. So percent composition, how do we compute this one? So we have NH4NO3. Let's try to compute individual atomic mass unit. Let's start with nitrogen. So we have 2 nitrogen multiplied by 14 because it's the atomic weight of nitrogen. So you have 28 ammo for nitrogen. Then for hydrogen, we have 4 multiplied by 1 atomic mass unit. So we have 4 ammo for hydrogen. How about oxygen? For oxygen, we have 3. Atomic mass unit of oxygen is, as I've said earlier, it's 16 because 8 atomic mass number is 8, 8 proton and 8 neutron. So 3 times 16 is 48. Now, the percent composition of nitrogen now is 28 divided by the total. What's the total here? 28 plus 4 is 32 plus 4. We have here 80 ammo. So the percent composition of nitrogen is now 28 over 80 multiplied by 100%. 28 over 80 multiplied by 100%. So it's around 35%. Do we have that in our choices? Oh, that's letter C. Okay. So good thing I memorized all of these before. I don't have the help of the presentation. I can still forget about the aluminum perlite. 27. So next is, given the formula mass of oxygen is 32, determine the number of moles in 52 grams of oxygen. So formula mass means we know that oxygen is, for oxygen, this is 16, right? The atomic weight is 16, but it has a 32. So meaning the formula for oxygen is now O2 because we need to multiply 2 amounts of oxygen, which is 16. That's why the formula mass is now 32. Determine the number of moles in 52 grams of oxygen. So now the number of moles is the number of mass over molecular weight. So we're not just considering 16 ammo, we will be considering the formula mass of 32. So the mass is now 52 grams. divided by 32 gram per mole. So grams will cancel 52 over 32. We now have 1.625. So the number of moles is 1.625. Do we have that in our choices? So these grams will cancel 1.625 or around 1.63. That's the letter C. Okay. Next, how many grams are there in 3.2 moles of calcium chloride? Here's another problem. What's the atomic weight of calcium and the chlorine? Chlorine is 35.45 earlier. So we have two. Right now, I need the calcium. So presentation, help me out here. Okay, calcium is 40 and chlorine is 35.45. So how many grams are there in 3.2 moles? So at first we will compute hmm, um, the calcium chloride, which is CaCl2. We have chlorine 35.45 times 2. And then calcium is 40 times 1. So 35.45 times 2 is 70.9. Then we have 40 here. 70.9 AMU and 40 AMU. We have 110.9 AMU. So that's in terms of gram per mole, that's 110.9 grams per mole. Question here is how many grams are there in 3.2 moles? So using the formula earlier, well, actually you don't need the formula. I'm guessing you just need to consider the unit. In order to answer the number of moles, you need to multiply the number of moles, which is 3.2 moles. Okay? In order to get the mass. So 110.9 multiplied by 3.2. That's how you get your around 355 grams. 355. Okay, if you want to use the formula, well, number of moles is mass over molecular weight. So you basically need the mass, just cross multiply. It's number of moles multiplied by molecular weight. As I've said earlier, the unit of molecular weight is gram per mole, and you want to cancel mole, so you just need to multiply the number of moles there. Okay, if you divide it, mole will not cancel. That's how I consider solving the mass without the use of the formula. Okay, I hope that makes sense. It's letter B, 355. Next, another chemical calculation is the empirical formula. So it's a formula that gives the simplest whole number ratio of atoms in a compound. So let's talk about empirical formula later when we have an example. Well, this is the step. Start with the number of grams of each element. Convert the mass of each element to moles using the molar mass from the periodic table. Divide each mole value by the smallest number of moles calculated. Round to the nearest whole number. This is the mole ratio of the elements and is represented by subscript in the empirical formula. Okay. So mole ratio is the subscript. Like for example, oxygen, you have O2. 2 is your mole ratio. Okay. So let's have that later, for example. But molecular formula, I guess it will be the same as the empirical formula, but um, once the empirical formula is found, the molecular for a compound can be determined if the molar mass of the compound is known. So like for example, NH3. So for a molecular formula, empirical formula or NH3 is empirical formula. And 2H6 is molecular formula because it has the same ratio for NH3, but it has a subscript of 2 and 6, meaning the molar ratio was multiplied by 2. Okay, that's how you deal with the molecular formula. So, steps in determining the molecular formula. Find the empirical formula. Next, find the mass of the empirical unit. Divide the molecular mass of the compound by the mass of the empirical formula. And multiply all the atoms or the subscripts of the empirical formula by this ratio to find the molecular formula. Okay? Like for example, as I've said, the when you compute the empirical unit and when you divide it, you get a value of 2, then you multiply that to the subscript. So that mole ratio, for example, is 2. You multiplied it with 1 for nitrogen and then 3 for hydrogen. You basically have this one as your molecular formula. Okay? So these are review questions for the next calculations, but how do we consider this one? The chemical formula, which shows the relative number of atoms, is known as the empirical formula. This is what I've said earlier. This is your empirical, this is your molecular formula, okay? It should be relative number of atoms. We're not basically multiplying it to the number of mole ratio. The chemical formula which shows the exact number of atoms is now this is your molecular formula, right? So as we mentioned earlier, after computing the empirical formula and you have the mole ratio of 2, you multiply it to their subscript, and this is now the exact number of atoms of the given element in a formula. Okay. So, okay, calculate the empirical formula of glucose, a simple sugar. We have carbon, hydrogen, and oxygen for glucose. Okay, so it contains 393.4 grams of carbon. Let's just write it down. 393.4 grams of carbon, 66.07 grams of hydrogen, 66.07 grams of oxygen, or hydrogen rather, hydrogen. Then 524.2 grams of oxygen, 524.2 grams of oxygen. So if you can review again the steps in determining the empirical formula. So this is how it's done. You get the number of moles of each element. Okay, so for carbon, number of moles of carbon is now 393.4 grams over, carbon is 12 gram per mole. Okay, so we have here how much? Using my calcu, or I'm just gonna write them down first. The number of moles of carbon here, number of moles of hydrogen, number of moles of oxygen. So this is a 66.07 grams over 1 gram per mole for hydrogen. The other one is 524.2 grams over oxygen. That's a 16 gram per mole. Now we will compute. Okay, individually, but I have this one already, 66.07 moles. And then next, 393.49 divided by 12. It's around 32.79 mole for carbon. And then 524.2 divided by 16. Again, it's around 32.76. So 32.76 mole. Okay. In these steps, after getting the moles, you get the lowest value and divide it with the number of moles of the given element. Like for example, the carbon. So you divide 32.79, divide 32.76. So this is your reference now. Then 66.07 divided by 32.76. And the last one is 32.76, divide 32.76. So this is exactly 1 because that's our reference. This one is around 1. 32.79 over 32.76. Okay, around 1. So the next one is 66.07 divided by 32.76. I guess that's equivalent to 2, almost 2. So what does it mean is that it means that we have one carbon, two hydrogen, and one atom for oxygen. In terms of empirical formula, you can write it down as C1H2O1, or this is CH2O. CH2O is now letter B. That's our answer. Okay. Whew. That's a classic one. Anyway, let's try to move on to, I guess it should be um, empirical formula again. But this time it's in terms of percentage. So empirical formula of compound of 52.9 carbon and 47.1% of oxygen. So what we call this? 52.9% of carbon and 47.1% of oxygen. Okay. So let's try to get the number of moles. For carbon, like for example, carbon 12, multiply this with 0.529. And then for 47, for oxygen, that's 16 times 0.471. So these are not yet number of moles, but these are atomic mass unit. So let's try 529. It's around 12 times 6.348. And then 16 times 0.47. 7.536. Okay. Mm-hmm. Oh, I guess we can try. I'm not seeing that this may be the solution, but let's try the other way. Like we'll try to compute the percentage of carbon in C3O2 if that is the same with 0.529% and oxygen is 47.1%. This will give us our answer. So what do you mean by that, sir? Like for example, C3O2. This is 16 times 2 and then carbon 12 times 3. Okay, we have this 32 and this is 36. So total we have 68. So the percentage of oxygen is now 32 over 68. That's a 47.1. So for carbon, it's 47 point, or for oxygen, 47.1%. And for oxygen, that's a 36, 52.9. Luckily, I'm not seeing that I can solve this one using computation of their individual atomic mass units. That's why I try another one. So this is our given, I guess. 47.1 for oxygen, 52.9 for carbon. So letter A will be our answer. All right, that should do it. So I guess I can try it out another example, but for now, that will do. We'll have number 31. Calculate the molecular formula of a compound with empirical formula CH2, and the atomic mass unit is 98. Okay. So how do we get the molecular formula? First, CH2. Get the atomic mass unit of CH2. Okay. For hydrogen, we have 1 times 2. Then for carbon, 12 times 1. We have 1 atoms for carbon and 2 atoms for hydrogen. We have this one as 2, and then this one is 12. We have 14 gram per mole. Okay. Now, originally, the problem is the molecular mass is 98. So the molecular mass is 98 gram per mole. And we need to get the mole ratio by dividing 14 gram per mole, which is the original CH2. So 98 over 14 is 7. So this is your molecular mass or ratio, which is 7. And as I've said, or from the steps, these 7 will be multiplied by the individual number of atoms here. So therefore, our answer for molecular formula is C7H14. Okay? 14. So letter A. Well, I guess what I can also mention here is that the only possible answer in number 31 is either A or D, because CH2 is 1 for carbon and 2 for hydrogen. For a molecular formula, the other formula must be proportional. I mean, you can have, oh, C2H8 is also wrong. I thought it's a C2H4. So C2H8 is also wrong because when you multiply 2 for carbon, you should be having a molecular formula of C2H4, not C2H8. So this is wrong. C7H12 is also wrong. CH7 is also wrong. Our only viable answer here is C7H14, which is when you multiply it by 7, this will be converted to C7H14. That's it, which is actually our answer as well when we solve it, when we get the mole ratio. Okay? So, well, that's for computation for now, and this blank space indicating that I need to have a break. Okay, so this will cut our video. I'll just continue for the next slides later. Okay, thank you.